Getting from A to B. The first thing that we see is a Jenga tower with numbers on each of the rows, as well as some Jenga pieces in the front that have numbers on them, some in the back that don't, and then one being held by a hand that reads 2023. The text reads, "We're making a tower. Initially, nobody thought out the huge energy needed. There have been some negatives along the way, but also some positives. But we've powered through it one way or another, and things are looking up. As you can see, rows 1 through 7 have already been built, and we've got the next 9 figured out as well. However, I found this one piece near the bottom of the bag. I'm having trouble figuring out where it will go. Can you determine the first, lowest row where it would make sense to place it?" Oh boy, this is going to be interesting. If you haven't already, I encourage you to give it a crack before watching, since solving a puzzle on your own or with others is always more satisfying than just seeing the answer. And even if you don't solve it fully, it will give you more appreciation for the solution. Jumping into it, this is one of the months where the Jane Street puzzle is really 2 puzzles. One, figuring out what in the world the puzzle is even asking, and then 2, solving it. To tackle the first half, we can start with a few connections that seem probable. The tower we are building is this Jenga tower. Each row corresponds to a number, since there are 7 numbered rows built and 9 numbered pieces on the table. And we're trying to figure out the first row we can place the number 2023 in this tower. From here, nothing else is entirely clear, so our only real hope is to throw mud at the wall and see what sticks. This involves staring at the text and picture with befuddlement and disgust, repeating phrases over and over, hoping something jumps out, and grasping at any connection we can find. Could it somehow be about a power tower? Maybe even an infinite one? Or maybe it's about getting from one arrangement of this Jenga tower, A, to another one, B. No, I got it. If you Google Jenga tower, one of the first things that comes up is the Jenga tower building in New York City. So if we go from A, Jane Street headquarters, to B, the Jenga tower, then once we are almost there, we see this bike station, which looks like infinity. And then 3 bus stops right here. And then Studio 27. And if we keep going past the Jenga tower, we have 2 hands, and 6th Avenue, and finally, it splits into 2 streets. Oh my goodness, it was so obvious. I don't know how I missed this earlier. Definitely onto something here. All right. Maybe I was forcing things a little bit, and you didn't come to hear about my unhinged descent into madness as I tried increasingly desperate ideas. So let's get into actually solving it. After staring for a while, I noticed something. All these letters at the beginning of each line started to stand out. Putting them together, we get WITAH. Let's see if this means anything. Yeah, that sounds about right. But just as all hope was nearly lost, when I came back the next day, a gift had descended from the puzzle gods. There was more text. Even quite useful approaches look suspect, adding tons of thought heretofore even beginning. Okay. Even though this text is equally confusing as the rest of the puzzle, luckily, as it turns out, we weren't far off looking at the first letters, but it was in the wrong spot. With our attention redirected to the second line, if we take the first letter of each word, we see N to the N equals A to the B. N to the N equals A to the B. All right, now we're getting somewhere. This can't be a coincidence, right? But what does it mean? After stumbling around a bit longer, we find a foothold in the fact that there are infinitely many ways to write 1 to the 1 in the form A to the B. 1 to the 1 equals 1 to the 2 equals 1 to the 3, yada, yada, yada. Which could explain the first row, n equals 1, being infinity. Let's check the next few rows. It seems to work for some rows, but not others. But then we think back to the text. There have been some negatives along the way, but also some positives. Do you see it? Everywhere there is an even exponent, the base can be positive or negative. And when we take this into account, we see perfect agreement. Now let's see if the pattern holds for the next 9 rows that have already been figured out. And sure enough, it looks like we found the problem. What is the smallest n such that there are 2023 ways to write n to the n as a to the b for integers a and b? At this point, we can let out a sigh of relief, or maybe shudder with further anguish, as we put down the mud we've been throwing at the walls and start to tackle a well-posed math question. It's not immediately clear how to proceed from here. One might be tempted to start brute forcing all possible power representations of n to the n. However, by the time we are at n equals 100, n to the n is already a Google squared, 1 with 200 zeros. So we'll have to resign ourselves to being more clever. To do so, we can start playing with a natural first step to gain intuition. Given n, determine the number m of integer pairs a, b, satisfying a to the b equals n. Let's go ahead and start with an example where n equals 2,985,984 and find a method for determining how many power representations it has. If we look at the prime factorization of n, then we can start to see a path to enumerating the various possible exponents. If there is a common factor between all of the exponents in the prime factorization, then we can use exponentiation rules to pull that number out. This immediately leaves us with something in the form of a to the b, like we wanted. So if we can find all of the common factors across the exponents, then we will find all of the possible exponents b. Again, we must remember to double count the even exponents. To systematically find all of these exponents, we will start with the greatest common divisor of all of the prime factor exponents, which we will call gamma. Then, if a number is a divisor of gamma, then it also divides all of the exponents and is thus a valid b value. So to find all of the possible forms a to the b, we simply need to count all of the odd divisors of gamma and double count all of the even ones. Therefore, for a general n, we take the prime factorization, find the greatest common divisor of the exponents, and then the total number of power representations is the number of odd divisors of gamma plus 2 times the number of even divisors. Equivalently, this is the total number of divisors plus the number of even divisors. If the number is odd, then there are no even divisors. And if it is even, then we can count the even divisors by counting the divisors for gamma divided by 2. Here, sigma 0 is just standard notation for the number of divisors. But this just punts the question to how do we count the number of divisors? We again turn to the prime factorization. Any divisor of gamma will only be made up of the prime factors of gamma, with all of the exponents between 0 and that original exponent. Thus, picking a divisor comes down to choosing exponents for each of the prime factors, which leads us to beta 1 plus 1 times beta 2 plus 1, and so on and so on. Now that we have a way to count the number of divisors, we can plug this into our function that double counts the even divisors. Altogether, this gives us a way to get the number of power representations for any generic n. We find the prime factorization and take the greatest common divisor of the exponents. Then we take the prime factorization of the greatest common divisor and use those exponents to obtain the final count. This procedure, although convoluted, reveals the way to reverse engineer the process. We want m equals 2023, and for now we can assume that gamma is even, such that 2023, which is equal to 7 times 17 times 17, is equal to 2 beta 1 plus 1 times each of the other exponents plus 1. Since there are only 3 prime factors in 2023, beta 4 and larger must be 0. We have multiple choices for the remaining betas, but we can start with beta 1 equals 3 and beta 2 and 3 equals 16. Thus, any gamma of the form 2 to the 3 times q2 to the 16 times q3 to the 16 will satisfy m equals 2023 for q2 and q3 prime. With this pattern, we can return to the original question we were after. For which n to the n are their 2023 power representations. If we raise n to the nth power, then all of the exponents will gain a factor of n, which we can then pull out of the greatest common divisor. This expression forces that n only has 3 prime factors, and they must be equal to 2, q2, and q3. If we find an alpha 1, 2, and 3 that satisfy this equation, then we have found a row where we can place the 2023 tile. The most obvious solution is alpha 1 equals 3 and alpha 2 and alpha 3 equals 16, since the greatest common divisor term is simply 1 in this case. However, if we decrease alpha 1 to 2, then the equation is still satisfied since the greatest common divisor is now 2 and replaces the factor of 2 that we just removed. It turns out that if we plug in the next two smallest primes, 3 and 5, then we have found the smallest n where n to the n has 2023 representations as a to the b. We can check this by finding all possible forms of n, by going back and finding all possible choices for our betas. Once we compile the full list, we see that our answer is indeed the lowest row. So hopefully you have a steady hand and some spare time, since by the time we place this 2023 tile, our tower will be a casual 41.7 light years tall. No question about the huge energy needed now. Thank you for listening. Check out my channel for more Jane Street puzzle solutions and come back next month to see if we can make sense of another one.